Something to look forward to.
You don't sound like you're being.
Huh?
You're being serious, aren't you?
I am being serious. So,
when, like, when you do the multiplicity, you just don't know what side's going to be negative or positive first. You got to plug in.
yeah.
Some,
The nice thing is,
you just
if you use
plug in
multiplicities, you only have to plug in one test point.
Right. But
Here, you can't really use the
you
ideal.
plug in a number like a negative to the left of that number. You see what I'm saying?
Yeah.
And then if you get negative, the multiplicity on the other side is going to be positive.
Well, the multiplicity would tell you what the other side is.
Right.
If it's going to change sign or not.
Mhm. But since it's just one, it switches.
Well, again, this is not, multiplicity really comes about from something like that, where it only shows up once
Yeah.
versus twice. You can kind of extend the idea of multiplicity to this, but it's pretty cool. This is the problem. It doesn't want you to graph it at the end. This is just purely asking you for the intervals where it's increasing, decreasing, the intervals of concave, up, down, so forth. Increasing, decreasing, first derivative. We found a critical number, right? What's definitely on this side of the critical number? No, that's where it gets a little tricky. Which side of that critical number is 0, 1? What is 1/3 natural log of 1/2? Yeah, why is it going to be a negative number?
Because the fraction you're taking.
Natural log of 1 is 0. So I'm below 1 for the input, so it's below 0 now for the output. So it's going to be negative. So 0 is actually on this side. So here's where it's 0. At that critical number is where the derivative is 0, so that's where it's flat. Now I want to check out both sides of it and see if it's increasing on one side, decreasing on the other side, whatever. So if I plug a 0 into the derivative, what do I get? If I plug a 0 in, what do I get? 2 times 1 minus 1? 1. Incredible. So more importantly, I get a positive number, right?
I was ignoring that too.
It's almost too easy. E's are evil, because when you start plugging 0 in, you can't just assume everything goes to 0, because they don't. E to the 0 is 1. What's below 1/3 of natural log of 1/2? I don't know. What is?
Negative.
I'll bet you negative 18 billion is below it, but I don't want to go there. What is 1/3 of natural log of 1/2? Is anybody able to do that for me? Negative 0.23. Cool, so negative 1. You think? Alright.
No, that's correct, yeah.
Sounds about right. So negative 1 is below there, right? So what do you get when you plug a negative 1 in? 2e to the negative 2 minus e to the first. Yeah, it's going to be negative, right? It's 2 over e squared minus e. So you're going to get a very small number minus e, so that's going to be negative. Cool, man. So where is it increasing? Yeah, that thing.
1/3, yeah, to infinity.
Infinity.
And then it's decreasing from negative infinity to that thing.
Exactly.
Correct terminology.
Because, of course, from the beginning, what was my domain for this function? Don't make too much out of it. What's the domain of e to the power? All real numbers. Right? I can take all real numbers in. No problem. So it's increasing above that, decreasing below that. So what is here? What is it that's there? What would we call that point? What is it?
That's our, because...
Is it a max or
It's a
min?
min.
Because it goes down to it and comes up from it. It's going to be definitely a min.
It's the mix now.
Alright, and let's see what else they say here. Find the local max and min. Is there a max?
No.
No, there's only one critical point. Right? It's not an absolute max or min question. So it can only be one local max or min, and it happens to be a min. And how do you find that point? What's the...
You plug it back into the f of x.
I love it. So you get 1/3 ln 1/2. And when you plug that in, let me see. So what is f of 1/3 ln 1/2. Well, that's f of ln 1/2. Get out of there. To the 1/3. Oh yeah, well screw it, you can just plug it in your calculator, but since I have e's here and I have ln's there, I should be able to do that by hand. So this would be e to the 2 ln 1/2 to the 1/3 plus e to the negative ln 1/2 to the 1/3. So I can bring that 2 up. I get 1/2 to the 2/3 plus, bring the negative 1 up, plus 1/2 to the negative 1/3. Oh
the
yeah.
lns cancel out.
Funky. And this is the point where you go, screw it, let me just put it in the calculator. Because this would be the cube root of 1/2 squared. Oh god, it's gross. Yeah, so whatever that thing is.
1.9.
Thank you. So you got a minimum at that, comma 1.9 roughly. So that's part A is increasing, decreasing. Part B was find the local max and min. And part C is all about concavity. So what do I have to do for concavity?
You need to take f double prime.
Yeah, take the second derivative. So for concavity and inflection point stuff, find the second derivative. Not too bad, all right? What's the second derivative here?
4.
Yeah, another 2 comes down.
4e the 2x plus e the negative x.
I like it. No, the negative comes down, makes it plus, and then you set that equal to 0.
Right.
All right. How's that? Is that all right?
That's
It's
that.
not that big a deal. It's almost exactly the same word for that. In this case, the derivatives look a lot like each other. Now here, this is interesting though. Let's see what happens here. Set that equal to 0. Bring that over. Multiply both sides by e to the x, and I get this. And what's interesting about that?
Change signs.
You divide by 4.
What's the smallest output you could possibly get from an e to a power?
1.
Yeah, not even 0. It's just right above 0, right? The smallest possible, because of course it looks like
Oh,
this.
yeah,
So what's it saying? It says 4 times something that's always above 0 equals negative 1. So what's the answer to that equation? Does that? I love it. No solution. There's no answer here. So what are the second derivative's critical values? There are none. Just fine. You don't have to have critical numbers. You don't have to have your derivatives equal 0. It's just where they're equal to 0 or undefined. That's where things get interesting. So there's no
cup up, cup down.
critical numbers. No. What is a second derivative's critical number? What could it possibly be? Inflection point. And what's the inflection point? What happens at the inflection point?
Cup up, when a cup up and a cup down meet.
Where the concavity changes,
Yeah.
right? So all that means is that the concavity does not change. That's all it means. And it sort of shouldn't make any... I mean, what's an E look like? An E looks like that. An
Yeah.
E function is always cup up. Eternally. Cool. Because, I mean, it's almost... I mean, the beautiful thing about E, here's its derivative, here's its second derivative. Does it have any critical numbers at all? Can E ever equal 0?
Not even
No, so this, E itself has no critical numbers. The reason this had, at least for the first derivative, is because it's got some, it's not just E, it's got some weirdness going on. So it does have min, but it's always cupped up. So it probably looks something like that, where it has a min, but it's always cupped up. Yeah. Is that cool? I mean, so don't think that everything we've seen so far always had critical numbers. But when I set these to 0, it doesn't have to have an answer. It doesn't have to have a real answer. So I might end up having no critical numbers. If the first derivative had no critical numbers, what would that mean?
That means that it's a straight line.
Constant.
Not constant, but the slope
always positive or always negative.
Or, yeah.
Never change the sign. It's either always increasing or always decreasing. Right? That's all that would mean. So the second derivative means it's always concave up or always concave down, if there's no critical numbers. You with me? So the critical numbers are places where things might change. So even if I have critical numbers, things might never change, right? But if I don't have any critical numbers, things can never change, because they could only change at a critical number.
Right.
Sweet. I got at least one person that understands. So I'm okay with that. Yeah, follow up this or
No, I don't.
whole other thing? I'll come back to you.
Along those lines.
Yeah.
I'm just confused about when can you have, like on 4.1 there was a set of problems that's like, sketch a graph of a function that has a local, it gives you the domain, it has a local max, but no absolute max. How can it be local but not absolute?
So which one's that?
Number
12.
Oh yeah.
Is that just because the absolute's not in that domain, or?
Well, no. You gotta. So let's see. Let's see what kind. I can take all this off here. So they want you to go from 1 to 2, right?
Negative 1 to 2, but yeah.
Oh, negative 1 to 2. Okay. So negative 1 to 2. And they want you to have a local max but no absolute max, right? So,
And vice versa.
well, yeah, part A says the other way. The other way is easy, possibly. To have an absolute max but no local max.
So like a line segment, and that'd be
How do you mean?
Horizontal line.
No, because then it would actually, there still is a max. There still is a local max, because local maxes occur where f prime is 0 or f prime is undefined. Okay, cool. Because I could have a local max that either is like this, and of course the same thing for min. Right? Max, min. Or I could have something like this,
right.
where the derivative here is not defined. That's a cusp. But still, that's a local max, right? So for part A, it's easier, because to have an absolute max but no local max, that's part A, right? That means that you have a maximum only at an endpoint. So that's why I was wondering what you meant. This would be like,
That's exactly what I drew.
I like it. Because there's no local max. There's nowhere where this thing has a horizontal tangent line, but at an endpoint it has a max. That's an absolute max. I like it. Part B is the other way around.
Right.
Part B says a local maximum, but no absolute maximum. So then I would have to have a place where the derivative does go to 0, or it's undefined, but somehow there's no absolute max. There's no biggest number. So think about that. What?
A horizontal line?
You have a line that's got a hole in it. Ours got a hole in it.
Have the local max higher than the what's it called? Yes.
There's like two things that equal.
No, then there would just be a tie. So they would both be the absolute max.
What if there's like an open circle
At the end.
at,
So what does the term max mean?
The highest point.
And so, it's the same idea as, in fact, I don't know if I made a big deal of this before,
It
but
goes from negative to positive.
if maximum implies, and the minute I say this, you guys are going to get it, which is fine. Maximum implies a ceiling. You hit that ceiling somewhere, that's the maximum. So to not have an absolute max means you don't have a ceiling, which must mean a vertical asymptote. So if you had a vertical asymptote, let's say here. So now I'm trying to remember. So it said you have a local max. So there's a local max, but no absolute max.
okay.
Yeah. So when you first come at that problem, it's like, how in the hell? Because anything you can imagine, it's like, if this is a local max, how the hell could it not be an absolute max also? I mean, if I go above it, then that's the absolute max. Holy shit, what do I do? You just keep going up. That's the answer. You just go crazy.
Well, is it possible to have, like, let's say at 2, it's an open circle, but it's higher than the local max? Is that...
What did they say? They didn't put any restrictions on here, did they? Yeah, they didn't say anything about if it's continuous or not through there. So say it again. So if it had a...
So like at that line, well, for example, using that example, that's fine. And then just once it hits x equals 2, it's just an open circle, but it's higher, the open circle is higher than the local max.
Well, you got to be careful. In that case, there would be no local max. Because
I mean, the open circle is at the end.
Take
At
the
X
arrowhead
equals
off of your arrow.
Oh, yeah, I see. All right, well, let's see.
That's what I did, but I wasn't sure if that's like correct.
Like it's going to be like this.
Once it goes to X, yeah, then yeah.
Yeah.
But there's still defined values that are above the local max there.
But, I mean, that's a good point. That's...
But the derivative isn't 0, that's the thing.
That's getting a little, so there is going to be, an absolute max does exist. It's like if this is 4.
Arbitrarily close to 4.
So it'd be like, I'd say the range for this is, whatever the hell that is, let's just make something up, -3 to 4, right? So that idea saying that it's the number that's the closest number to 4. So, but that's a really, I like that idea. That's where things get a little weird in mathematics, is if you're the next number away from something, does that number even exist? Now, let's not even get into that tonight. But I like that idea. But I think technically there you have an absolute max.
But the slope's not 0 or undefined.
That's no problem at absolute max.
Oh, only on local?
Local maxes and mins have to have a horizontal tangent line. Yeah.
Got it. That's right.
Okay. Anything else from homework? Okay. All right. I'm optimistic fool as always. So that means everything's going great. So what we did last time is related to that sheet I gave out. And just to kind of recreate this, I want to kind of do this live with you, even though you have it right here. Just to summarize everything we found, and I want to show you how I came up with that beautiful graph. So we got the max was 150,000, min 30. Let's see what else we got. We got blah 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 blah. Inflection point at -3/2, 0, 0.21, about 28,326. 1.79 and about 26,414. And then, okay, cool. So if you, and of course the intercepts and all that, so I got x-intercepts, 3, 0, and -3/2, 0, and y-intercepts, 0, 19, 683. Okay, so to do this, if you do this for yourself, it'll make this such an easier problem. If you, first off, pick a good scale. So I picked 10, 20, 30, 40, 50,000. Blah, thousands. My scale on the x-axis could have been a little bit better, but I'm okay with that. Okay, so 1, 2, 3, -1, -2, -3. I think it's far enough, right? How are you? Yeah, you're good. Okay. So if you label, and I said this last time, but we only did one example. If you label your points, so when you graph this, here's the, it's a min, no, it's a, where am I at here? Oh, there you go. So -3/2, 0 is an x-intercept, but it's also an inflection point. 3, 0 is just a min, and it's a x-intercept. The other inflection points are 0.21, 28,000. So here's 0.21 is about right there. 28,000 right there. And then 1.79. So this is inflection. 1.79. And then 26,000. So just a little bit below that one. That's an inflection. Okay, I think I got everything. Max is up here. The max is 150,000. Okay. So if you label your points as you go, it'll tell you what to do as you hit each point. So I know it starts off increasing, and I know it starts off concave down. That's all I really need to do this. So it starts off concave down and increasing. There's concave down, increasing. And then this is an inflection point. So what's going to happen there? It's going to, yeah. And where's my y-intercept? I forgot to do that. 19, so it's about right there. Okay. So now it's concave up, still increasing.
It's going to change again.
And now here it's going to change to concave down. That's the max, so I know not to go above that. And now it's going to change to concave up. Touch that. Go. So after teaching calculus a couple times, where I tried to have like the intervals here, and then we kept referring back to that, I finally realized if you just freaking label your points. I couldn't even remember how I did it when I took this way a long time ago, but if you just label your points, as you hit a point, it tells you what to do. It's silly. And you don't have to know about increasing, decreasing, because if the next point's there, you're obviously increasing, right? Yes, sir.
Can you remind me one more time, how do you know when you're increasing or decreasing? Is it just by the timeline thing that you do?
So what calculus do I do to get the slope? Derivative. So if the first derivative is negative, that means the slope is down. So it's decreasing. If the first derivative is positive, it's increasing. Is that simple? Yeah.
Okay.
Cool. All right, so how do you guys feel about that? Is that all right? Yeah.
For the inflection points, you plug them into second derivative? Or?
Oh, to get the other part of the point?
Yeah.
So whenever you want to know where the point is, where to actually plot it, you have to plug it back into f. You have to plug it back into the original.
Okay.
If I plug it back into the second derivative, I'm going to get 0, because that's where they came from, right?
Yeah.
And if I plug it into the first derivative, I'm just going to see what the slope is through that point. But I want to know where the hell to put the point. Whenever you want to do that, you have to put it back into the original.
Yeah.
Yeah. And I think I told you that almost since day one, when we first started talking about derivatives. You're going to get to a point where it's f and f prime, and now f double prime. You got to know when to use which one. Cool. Yeah.
So really, the only thing that we're plugging back into the derivatives are the zeros to tell us if that derivative in that section of the timeline is positive or negative, right?
Pretty much to create your sign diagrams, you're just plugging in points into that, and that's almost the only time you're going to plug anything in there. Now, if you apply the second derivative test and you're plugging in critical numbers from the first derivative, right? You guys remember that? So here, if I wanted to apply the, oh boy, let's see. If I wanted to apply the second derivative test, so f double prime was disgusting. You all have it there on the paper, so I'm just going to do this for my own reference. So if I wanted to do the second derivative test, what's the point of the second derivative test? What does it take the place of, in a way? The sign diagram for the first derivative, right? Because what does it tell me? The second derivative, of course, tells me concavity. So if I know the concavity at a critical number is positive, what does it tell me about that point? It's cupped up, so it must be a minimum. You with me? And it also tells me it must be coming down to it and up from it. So it gives me some information there, right? So it kind of takes the place of the sign diagram that we can make for the first derivative. So if I investigate, so one critical number I got was 3. And of course, when I plug a 3 in, I get 0, right? And that was the one that's inconclusive. We had to do some other stuff, so I still need a sign diagram for that. But another critical number I got from the first derivative was negative 3 halves. And of course, that one is 0 too. Oh, well, we're just screwed all around. I think that was the only 0. Oh, and 1. Yeah, f double prime of 1 is positive, positive, negative. So f double prime of 1 is less than 0, which means it should be concave down here, which means that 1 should be the location of a max, and that's of course true. Right. So second derivative test is very useful if you only want very specific information. Is this point a max? Is this point a min? But in general, if it comes out to 0, it doesn't tell you a damn thing. And the sign diagram is very useful for seeing exactly where it's increasing, decreasing. So I would use the sign diagram more often than I would use this. But it's here if I just am curious about a single point. I can use the second derivative test. Yeah?
When a second derivative's critical number is from an even multiplicity, does that mean
evil? Say again?
Does
Sorry?
that mean, okay, so I have like right here 3. The critical number 3 for the second derivative is an even multiplicity. Now what is that?
Yep.
Does that mean that it's not an inflection point if it's an even multiplicity?
Yeah, because the sign won't change around there. Yeah. So the only inflection point we got, well, we got 3 inflection points because we got 2 numbers from here and they both were inflection.
Right.
Because they would each be a first.
Right, I understand.
And then negative 3 halves is an odd. Yeah, so that guy's not in that list. So yeah, any even multiplicity roots in your second derivative means they won't be inflection points. In your first derivative means they won't be maxes or mins.
Right. Does it tell you anything other than the fact that they're not inflection points? Like in this case, it just so happens that it is a minimum, like a local minimum. Does that mean that's what'll happen, or is it just because?
No, yeah, be careful. That's not necessarily true. That happens a lot though, because a lot of the functions we look at are polynomial in nature. And when you get these that have multiple factors, you're going to have this case where you have things that have multiple meanings. Let's see if so the 3 was there from the beginning. So it's going to be an x-intercept. It's still here, so it's going to be possibly a max or a min, and it could possibly be a concave, it could be an inflection point. So when you have something like x plus 5 to the 7th power times 3x minus 7 to the 8th power, when you take derivatives, those are going to be repeating. They're going to continuously be roots of all these different derivatives. So they're going to have a chance to be, but they're going to keep alternating from even to odd multiplicities, right?
Right.
So in a way, I see what you're saying, but be careful because
it's just coincidence.
Yeah, at some point you might take enough derivatives to make it go away. So I always just step back and look at what I got. Don't try to make too many generalizations. But that actually would work for most things, yeah. Anything else? Any other questions from that? Any other homework questions? All right. So we're going to get into section 4.4. And actually, I tell you what, we're going to do one problem. Highlight something. If I had this function here, take a minute and try to find its local max and min, and if there's any inflection points. Let's just do one thing right now. Let's just find the critical numbers for this, the first derivative critical numbers. So what do you guys get for the first derivative? Have you gotten there? What do you guys get for that?
3 over x plus 5 to the second.
No.
7, yeah. Gotta be careful. The evil thing there. Yeah. Yeah. I like, so almost. So it's 7 over x plus 5 squared. Is that ever equal to 0? Hell no, because the only way it can equal 0 is if the top is 0 and the top's always 7. So, but the other place where you get critical numbers from is also where the first derivative is undefined. So this guy is undefined. -5. But the big thing about this here, so 2 points I wanted to make. I wanted to really make it very clear because we've been focusing so much on simpler functions just to get the idea down that I really wanted you guys to understand that critical numbers not only come from where the derivative is 0, but they also come from where the derivative is undefined as long as it's in the domain of the original function. Now what's wrong with that point there? At -5, is the original function even defined there? No. So that's not even a critical number.
There'd be a hole there too, right?
Not a hole. There would be a asymptote. Notice something else. Can anybody tell me anything else interesting about that, considering it's the first derivative? Anything else interesting about that function that's related to the first derivative and what that would mean for the shape of the graph? 7 divided by something squared. Can it ever be negative? No. 7 is positive. Something squared is positive, right? So this is always bigger than 0. So this function is always
Positive.
increasing. Thank you. Yes. All right. Right. The first derivative is positive. That's where the function is increasing. This derivative is always positive, except of course at -5. It's where things get weird. How do you spell weird? Weird is weirdly spelled. Did that on purpose. You guys semi with me? Now, of course, if we remember our pre-calc, we already know something about this. What do we know about this? 2 things. Just looking at that. Vertical asymptote at -5 and
At 2, there's a horizontal.
at 2 there's a intercept at x equal 2, right? Y-intercept is -2/5. And one last thing. So there's more than I need to say. What's the horizontal asymptote? Somebody gave me an incorrect guess. What situation am I in?
1.
As x gets really big, it's 1/1, right? It's the ratio of the coefficients of those because they're the same degree. So this will be at 1. So since there's no intercepts back here, do you guys remember what that means? Remember, and again, this is why you went through pre-calc. So you'd have to worry about learning all this shit now. It's better just to have this coming in. Can it possibly be down here?
No,
Because there's no doors there, right? So it's got to be up here. And what's it doing over here? It's got to be doing this kind of weirdness here, right? I know it goes through there because the multiplicity of that root is odd, 1. So what's this function always doing? It's always increasing. Except at 5, at -5, it kind of resets. Going up forever, reset. Going up forever. Right? Now it's got a ceiling, but I don't care. I just get really, really, really close to the ceiling, and then I get even closer, and then I get even closer. It's always going up. That's kind of cool. So that's where the points I wanted to make were you have to look at where your derivatives undefined and include that number in your list of critical numbers, but you don't include anything that's not in the original function's domain. That kind of makes sense. That's out of the question to begin with. Cool? So a function that would actually have a critical value where it's undefined would be something like this. What's that guy's derivative?
1/3 x to the negative 2/3.
Look at that. What are the critical values? Is that ever equal to 0? No, it's 1/3x to the 1 can't be 0, so it's never equal to 0, but is it ever undefined? What time did you guys wait? This is 1/3x to the 2/3. What makes that undefined? 0. So critical number would be at 0. Is that in the domain of the original? Yes. So it's a valid critical number. So I do have to analyze it and see what's going on there.
What do you mean if it's in the domain of the original?
Is 0 work for this? Yes.
Yeah.
Over here, did -5 work for this? No. So I had to cross it out. It's not a valid critical number.
Oh, so you include it.
Include it, because it's in the list of what x could be in the beginning. Here, the list of what x could be did not include -5. What is happening? They're dragging an oarfish. Okay. So now you'd have to do all your analysis on this. And what's really going on here? And we know this. What's true at 0? What's the f prime at 0? If you try to plug a 0 in here, what do you get?
0.
No. Undefined. You get infinite, right? So right at 0, I'd expect this thing to kind of be straight up and down, just for a second. That's exactly what a cube root looks like. It looks like a square root with the other half of it there. So right here, it's kind of like straight up and down. It's a vertical tangent line for just a second. Not even a second, right? Just for that very instantaneous point, right when it's at 0. You guys with me? Sort of, okay. Somebody goes, I'm there, but my brain hurts. I understand. Okay. So what I want to focus on tonight.
Can you say that one more time? When you take f prime, you get the 0 or whatever?
Yeah, so critical numbers come from the x values that cause f prime of x to be undefined or 0 and are in the domain of f of x. Okay, so the critical numbers come from the x values that do two things. They cause f prime of x to be undefined or 0, and they're in the domain of f of x. If they're not in the domain of f of x, I would not consider them for anything. They're not things I could use in any way. Okay. And just to point it out, I don't know if they say it all together in one place. Yes, bottom of page 277, definition 6, where they define critical number. Okay. So any other? Yeah.
Critical numbers is different from critical values.
I keep using the same word. Yeah. Critical numbers, critical values. If I say them, they mean the same thing. Okay. So what I want to focus on tonight is section 4.4. 4.5 is really just another curve sketching section. So we'll see how far we can make it here tonight. Now, this section is, once students learn this section, they start to go, well, damn, I wish I would have known this a lot sooner. But we can't even talk about this section really until we have derivatives really under our belt. But they kind of go back and talk about limits. So it's a very cool way to handle indeterminate forms in limits. So if you're going any further in mathematics, you're going to use L'Hopital's rule a decent amount of the time. So that's what this guy, his name is L'Hopital. Very often you'll see the S taken out, but he spelled it like hospital, so there you go. We'll defer to the man himself. And the whole idea behind L'Hopital's rule is if I have a limit of, in fact, it doesn't even matter what it's going to. Where f of a over g of a is indeterminate. So I've used that word before. Who can remember what that means if it's to be indeterminate?
0 to 0.
Yeah, it could be in what form?
0.
0 over 0. All right, so that's one indeterminate form. What else? Infinity over infinity. I love it. Right? Now 0 over infinity is definitely not indeterminate. That is like really 0. Right? 0 divided by infinity is just like super 0. And infinity over 0 is like crazy infinity. You with me? So those are not indeterminate. Here, 0 divided by anything is 0. Anything divided by 0 is infinity. 0 over 0, I don't know what the hell. And what do we keep saying? And this is the key to the reason why L'Hopital should work. What tells me what it's going to be? How did we talk about this? For example, a very simple example that we use other ways to do, would be something like this.
The highest power.
And actually, not even that. I don't want to go there. I want to go here.
The highest power.
Yeah, maybe like that. Here we go. Yeah. So here I would just look at who's got the highest power. Now, why should that matter? Why really should that matter?
Because
What's the whole idea?
the top overpowers the bottom.
And flesh that out a little bit more.
The top gets bigger.
The top and the bottom, they're both going to what? Infinity. So this is infinity over infinity. But which one's getting there faster? The top one, right? So they both go to infinity, but the distance between the two of them keep growing. So the ratio of them is going to be infinite. So they both go to infinity, but they are getting further apart as you go up. So that's good. So somehow the rates at which these two go, which tells me what should I be using possibly, what should I be allowed to use here to figure out what this is. If I'm talking about the rates, how quickly these things are going, that implies what? The derivatives. I like it. So, considering that the proof of this is absolutely disgusting, I want to show you a truncated proof and see what you guys think. So let's say this is indeterminate. In some way. In fact, let's be more specific. Let's say this is 0 over 0. Right. Now go with me for a minute. And this is kind of cool. Remember when we learned linear approximation? I know that everybody made way too much of it, and it became this really difficult thing, but it's just finding the tangent line somewhere. But it's a way to take a function and make it into a linear function always, that only works close to a certain point, right? So it's really cool. You make a really ugly function become a very easy function, but the trade-off is, oh, it only works this far. Kind of a big trade-off, right? But still, if you only have to go within that much, you're good. Just use that straight line instead of the funky-ass function. So, near A, what does this look like? Remember, it's the form of this. So that's like y1.
X minus A.
And of course, g of x would be the same thing. Now considering that it's indeterminate, meaning when I plug an A in, I get 0 and 0, what's f of A and g of A?
0.
It's got to be 0. That's exactly why we have this problem, right? At A, these things are 0. So this and this, they're both 0. So as long as I am close to A, these are valid. Are you with me? That's the whole idea of linear approximation. If I can find a linear approximation, there has to be some area around A that linear approximation works. That's a good enough approximation. Are you guys, is that cool? But just by itself. I love you guys. Are you with me? Some of you look at me like you're angry. What happened? Makes sense. Is everybody decently cool with these two expressions? These two expressions are okay? Is everybody decently cool with the fact that these are 0? Because that's the whole reason why we had a problem in the first place. Was because they're both 0 at that point.
Would it still be 0 if it was a different indeterminate?
Exactly. That's why I want to start with this guy. All right? How we doing so far? Those two things, are those cool? Okay, so all I was saying next was these expressions only work if I'm really close to A, but what's the whole point of this? I'm getting really, really close to A. So I can take this expression and say that equals the limit as x goes to A of that. You with me? And of course what happens there that's really nice? I can't plug an A into x because it's 0 over 0, but these both go away. So this is basically saying the limit of f to g is the same thing as the limit of f prime to g prime. That's the heart of L'Hopital's rule. And why does that make sense as far as what we were talking about before? The limit totally depends on how quickly these things are going to infinity or going to 0, right? And that should be the derivative of each, telling me how quickly they're going there. The really cool thing about this is, not only can you get a feel for it, but just taking the derivatives actually gives you the answer directly. It doesn't just tell you who wins, it actually gives you the exact answer. It's kind of silly. Now, real quick, if like somebody just said, what if it was infinity over infinity? So if f of A goes to infinity, right? So that would be the limit as x goes to A, f of x over g of x. So this would be infinity over infinity. Cool? So what if I said, let t equal 1 over x? Just because I want to. Then what would f of t over g of t do? Oh, what would this be? 1 over a, maybe? Sure, why not? What would happen here then? I don't know if you guys can see this. Maybe a specific example will help. Yes, sir?
Would they flip? Would it become G over T over...
No. Because now I'm making the inputs different. So here, this input took f to infinity, right? So let me give you a specific example. Let's see.
Yeah, wouldn't it be 0 over 0?
Yeah, exactly. So, I mean, the proof we just used works for infinities also, because all I have to do is flip the input, and then I can use the same argument we just used. So the point is, this idea of, if I have this problem here, and it's indeterminate, 0 over 0, infinity over infinity, and we're actually going to learn a few more indeterminate forms. Those aren't the only two. But if this ratio is indeterminate, I can just take the derivatives of the top and bottom and then look at it again. And the beautiful thing is, if it works once, it works many times. So if it's still indeterminate, do it again. If it's still indeterminate, do it again. The biggest mistake that students make is to take derivatives when it isn't really indeterminate. If you do that, you're going to get the wrong answer. This only works if it's indeterminate. If it is determinate, then you're going to get something weird. So let's do a couple examples. Some concrete examples. Let's do limit as t as x goes to 0. Let me get it going. Let's do this one. Yeah. X goes to infinity. This is a really good example of the rate at which the functions are moving. So that's the first derivative. So the question of this really boils down to who's going to infinity faster, a natural log or a cube root? But first thing to check, before you take any derivatives, you have to make sure, is this indeterminate form? So if you try to plug infinity in, what would you get? No.
Infinity over.
Yeah, infinity. So I'll get an indeterminate form. So I'm allowed to use L'Hopital's rule. And so what does L'Hopital's rule say? I'm allowed to take the derivatives of the top and the bottom. So be very careful. This is not quotient rule. This is an idea. It says the limit of a ratio is the same as the limit of the ratios of the derivatives if you have an indeterminate form. So what's the derivative of ln x?
1 over x.
1 over x. What's the derivative of x to the 1/3?
1/3 negative 2/3.
1/3 x to the negative 2/3. I like it. Now simplify that a little bit. Try to simplify that a bit.
2/3 over 3x.
Yep, good. I like it. So it'll be x to the 2/3 over 3x. Now even take it a little bit more. Reduce that. What do you get? A whole x on the bottom, 2/3 of an x on the top. How much of an x is left on the bottom?
1 over x to the 1/3.
1/3 of an x is left. I like it. So it'll be 1 over 3x to the 1/3. And of course that is now determinate. Right? I can actually plug infinity in. Right? What does it go to when the bottom gets really, really big? The whole thing goes to 0. Bam. That's cool. That would have made a lot of our limit problems easier. All right, let's try another one. Let's see, blah, blah, blah. Oh yeah, let's try this one. That looks kind of freaky.
Wait. On the last step there,
Yeah.
You just drop the x to the 2/3.
Yeah, I mean, what do you do with powers? When you divide them, you subtract. So, you get 1/3 left on the bottom. Yeah, cool. What's the derivative? Well, first off, is this indeterminate? Yeah, what type of indeterminate is it? Yeah, 0 over 0, I like it. So I'm allowed to use L'Hopital's rule. What's the derivative of sine 4x?
4 cosine.
Good, 4 cosine 4x. Derivative of tangent 5x.
5.
I like it. 5 secant squared 5x. Is it still indeterminate? When you plug a 0 in, what do you get for cosine of 0?
0.
No.
1.
1, so you get 4 times 1 is 4. So it can't be indeterminate already. Now the bottom might be infinity or 0 or some number, but it's going to be determinate. I can figure out what the hell it is now. So what do I get when I plug a 0 into secant squared? Secant is basically 1 over cosine. Cosine of 0 is 1. 1 over 1 squared is times 5.
Fine.
Whew. All right. That made that problem a lot easier, right?
Yeah, dude.
Sweet. Now you guys try this one.
You said just to keep going?
So anytime you have a limit of something that's indeterminate, you can apply L'Hopital's rule. So there's nothing that says you won't have to apply it several times within a problem. If I apply it once and it still comes out to 0 over 0 or infinity, infinity, I can apply it again.
Just take the derivative again.
Until you get to a point where it's not indeterminate, where it's not 0 over 0 or infinity over infinity.
I thought double prime was when you're taking the rate of change within the rate of change.
It's true.
Product rule once you get down further.
So again, you got to be really careful about this. Is the quotient rule doesn't come into this, right? What's the derivative of the top
Secant squared x by 1
and derivative of the bottom?
or x squared x.
So is it still indeterminate?
Yeah.
Yeah, secant squared 0 is 1 minus 1 is 0. 3 times 0 is 0. So now, don't overthink this. I know that all the derivatives have meanings. It's awesome, and it's beautiful that you know it. But here, the limit of this equals the limit of this. And I still can't get the answer. It's still indeterminate. So then I apply the limit of this equals the limit of its derivatives. I mean, if it works for this guy, why shouldn't it work for this guy? So if they would have given me this problem to start with, what would we have done? We would have applied derivatives, right? Because it is indeterminate. Who cares that it started off there? Every time I have a new limit from applying L'Hopital's, that's its own limit. If it's still indeterminate, I should still be able to apply L'Hopital's rule, right?
Why are you on one leg?
Because I just am. I don't know why. So, if I apply L'Hopital's one more time.
Secant.
So this is what you're worried about here, right?
Yeah.
Good.
Tangent x.
So here, this is really secant x squared, right? So if you want to write it like that, it might be a good idea when you have these squares of trig functions or cubes or whatever. You might want to actually write it as a power, so that'll help you figure out what you have to do. So what's the derivative of something squared?
2 that.
2 times that thing, right? To the first power here, so that's that. And then what's the derivative of the inside? And of course, the derivative of 1 is gone over 6x. All right. Do you guys see that? So trig functions are a little evil. When you have like sine 7x, you should write it like that, and you can really see what it is. I mean, that putting that 7 in the middle is just shorthand. It's just a way to write it quicker. I don't need parentheses then. but it kind of hides it for derivatives. It's really easy to not realize what's going on. So I have to take care of that squared first, and then secant gets its turn. Now when I plug a 0 in, I still get a 0 on the bottom. That looks bad, but as long as the top is a number, I'll be okay.
Infinity.
Yeah, what happens to the top? This is 1 times 1
1 times 0.
times 0, so still 0. Isn't it?
Jesus Christ.
Jesus Christ.
So we gotta do it again.
But let me analyze this real quick. What do I get? 2 over cosine squared.
Now, would we do the?
Sine over cosine over 6x. So I get 2 sine. I guess it's still, yeah, it's all a problem. It's still going to be 0. Okay, too bad. So then if we apply it one more time, let's see what we got here. We got 2 secant squared x, tangent x. Now if you apply it one more time, what's going to happen to the bottom?
6.
It's going to be 6, thank God. So we got to get an answer now. And the top, yeah, it's going to be, now I've got a product rule and there's a chain rule here. So it's going to be 4 secant. Derivative of secant is secant tangent times tangent. Oh my God. So this part is from bringing the 2 down. This is the inside of this. That's secant getting its turn. And this is the tangent that I'm leaving alone. That's the product rule, right? So this is product, the derivative of the first part times the second part, plus the first part derivative of the second part. What's the derivative of tangent? Secant squared. So I get 2 secant to the 4th x. Oh my God. So when you plug a 0 into the top, what do I get? I get, this is going to be 0 because the tangents are 0, right? Plus 2. Whew. Thanks for that subdued clap. Freakiness. So that was even. So we went from only having to do one step to having to do several steps. But it's still a really powerful way to do these by hand, as long as they're indeterminate. So it's the key thing. So they're going to give you problems, and so will I, that aren't really indeterminate. Just like I gave you on the limit problems, I gave you problems where you could actually just plug the number in. But a lot of you guys were doing like conjugates and all this weird shit. You didn't have to. You only do that if you can't plug it in. You only do L'Hopital's if it is indeterminate. If it's determinate, that by definition means you could determine what the answer is. Okay. So, let me see if there's anything else. Oh yeah, there's a couple other freaky little things in here. Okay. Now, realize that secant is the one that goes with cosine. So secant looks like, this here is the pi over 2. So secant is going to be the one that sits on top of the cosine. And why is it important to realize that here? Because they're saying the limit as x goes to pi over 2 from below, right? Oh shit, all this limit stuff's going to come back. So if I go to pi over 2 from below, what's secant doing? Going to infinity. Good. Positive infinity. If it was from above, it'd be negative infinity. So that's got to have some bearing on this. So this is basically, this is infinity minus, and what happens at tangent, of course. That one's easier. That one's got the negative pi over 2 pi over 2. So it's going to infinity. This is infinity minus infinity, which you wish was 0. But again, it all depends on how quickly they're going to 0. I mean, how quickly, where that difference is going. How quickly is each one going to infinity? So it is a lot like a ratio. It just isn't a ratio. So I can't directly apply L'Hopital's unless it's a ratio. But what's the beautiful thing I could do here?
Make it.
Yeah.
Make
Make it a ratio by doing what? I can't do any derivatives because L'Hopital specifically applies to ratios of functions. Period.
Tangent x to the negative 1?
No.
1 over cosine.
Yeah, just use the basic definition. So I got below, so this will be 1 over cosine minus sine over cosine, so it's 1 minus sine over cosine. Right, they have LCD, which is beautiful. 1 over cosine minus sine over cosine. I get 1 minus sine over cosine. Is that indeterminate? It has to be, because it came from something that was indeterminate. So if I plug in pi over 2, I get 1 minus 1 over 0. So this is still indeterminate, just as a ratio now. So it sounds like a note. L'Hopital's rule only applies to functions that are in ratio form. I have to have a ratio of functions.
So you think the derivative of it again?
Yep, now you can attack it with L'Hopital's directly. Drew, the top would be negative cosine, negative sine. And when you plug a pi over 2, is it still indeterminate?
No, you get 0 over
0 over
negative
1.
I got negative 1.
Oh, the negatives cancel.
Oh, yeah, no.
We get 0 over 1, so the answer is 0. You're done. So that was one application of L'Hopital's. Once you put it as a ratio, you can apply L'Hopital's. So L'Hopital specifically says the limit of the ratio of two functions that are in an indeterminate form is the same as the limit of the ratio of the derivative. So it has to be ratios.
Why does that equal 0? Because isn't 0 over 1 something different from 0?
All right, now stop. Write it down.
Wait.
And look at it.
Huh?
Write it down. 0 over 1.
You have 0, 1.
I got it.
Okay, all right. Well, it's really easy. I don't mean to pick on you, but it's really easy to get like up here with all this all new shit and not realizing, no, that's very open shit. Yeah. One last form. What if I had this thing here? What do you got, Jeff? Okay. Which one do I want to do? Yeah. Let's do that one. Now, what's interesting about this one? When x goes to 0, x, incredibly enough, goes to 0. Why do I have to say from above? Because natural log only exists above, but as it goes to 0, what's the natural log do?
Going down.
Come on now, we have to know the basic shape of these functions, and it's going to go to negative infinity. So I have basically 0 times an infinity, which is another example of an indeterminate form. They can all be written, or not all of them, you got to be careful, but most of them can be written as a ratio. You can kind of work things around. Now, anybody have any clue how to write that as a ratio?
X over 1x?
I think you're trying to do a derivative at the same time. You can't do a derivative yet until you get a ratio written.
Change it base. I was thinking change it base, but I don't know.
No. I like the idea.
You bring E in there?
I hadn't even thought about that. Honestly. No, it still wouldn't work because the bottom would just be constant, so it's no good.
You can bring the x up to as an exponent.
Here's the weirdest thing, you guys would never think of this. If I force that down, what's it gotta look like?
Next to
There's the
negative
negative 1.
Yeah, or whatever. So you gotta see it at least once. Once you see it, you're like, okay, I got it. So if you have something of the form 0 times infinity, or who cares if it's negative, 0 times some kind of infinity, you can take one of them and just divide by its reciprocal. And now you can attack. Now, I could have taken natural log of x and made it 1 over natural log of x on the bottom. I probably would stay away from that. Right? Its derivative would actually be uglier than it is. So I want my derivatives to become nicer as I do this. So I can apply L'Hopital's now, because now this is going to be negative infinity over...
0. Oh, no.
Over infinity. So I don't know where that's going, right? It's still indeterminate. So I can apply L'Hopital's rule. What's the derivative of natural log?
1 over x.
What's the derivative of 1 over x?
X, 1 over x squared.
I like it. And of course that simplifies to be what?
One over negative x. Oh,
X, yes. So negative x, yeah. And of course, as that goes to 0, that goes to 0. What that's really saying then, and this should kind of make sense, and this, you start to realize what we're really getting at is this is an ability to compare the rates of change of functions. If x is going faster than natural log, x is going to 0, it's going to drag the whole thing to 0. So x definitely has a larger slope than natural log. Natural log is the slowest moving damn function there is, like the three-toed sloth of the function families, right? There I go. So x is definitely going to 0 a hell of a lot faster than natural log is. So the whole thing ends up going to 0. It kind of wins, right? It's going faster to 0 than natural log is to negative infinity. So it's going to... Okay, maybe, I don't know. Okay. Okay, I think that's all of them. On page 306, they kind of summarize all the different forms, all the different indeterminate stuff. Actually, this is more, that's more specific. I thought they did do it somewhere. Page 306 is actually the last type. Oh boy.
How come on, like, the secant x minus tangent x, on this last one I understand because we're at negative x, but so if we took the derivative of that, then it's going to become a constant.
Well, in fact, it's more than that. It's at this point, I don't have an option to do that at all. I can't.
Right.
It's not even an option because it's not indeterminate. Yeah.
What? So I guess I'm confused. Like on the one before that, secant x minus tangent x, we did it that L'Hopital's rule twice or whatever, and ended up with cosine x over sine x, which still equals 0 over 0. Right?
So we had secant x minus tangent x, which we rewrote as 1 minus sine x over cosine x. We only had to do L'Hopital's once. So the first thing we did was not L'Hopital's rule. What was this, pi over 2?
Yeah, pi over 2.
The first thing we did was not L'Hopital's rule. The first thing we did was just rewriting it.
Right.
Yeah. In fact, sometimes, I remember I used to do this, put a little LH when I actually applied L'Hopital's rule.
But I guess, then we end up with cosine x over sine x.
Then you just plug in 0.
And then that's not. I'm just confused.
So it's sort of like when you factor. You do one factoring step, and you step back and you say, "Can I do anything else?" And then if you can, you do it. You do more. So here, it's always what you're looking for before you keep applying L'Hopital's is it still indeterminate? That is not, because when I plug a pi over 2 in, I can actually determine what it is. So it's not even like how do I want to say this? It's not even like it's a small mistake, like you shouldn't have done it. Oops! It's like you cannot do it anymore because it's not indeterminate anymore. And if I do apply it, I'm actually going to go the wrong direction. I could end up with the wrong answer. So a really good example of one that gives you a wrong answer if you're not careful. It's something like, so if I just blindly go into this and I say, okay, so let me take a derivative, so I get cosine x over sine x. And as I go to pi, this is negative 1 over 0, so that's infinity. That's negative infinity. Yay! Next problem. Now, the person who does this is the person that focused way too much on the rule and not enough on the requirements to use it. Is the first problem, is that indeterminate? When you plug a pi in, what do you get on the top?
0.
0. What do you get on the bottom?
0.
No.
1.
1 minus, what's cosine of pi? Negative 1. So that's 0 over 2, which is 0. So the correct answer to this is 0. If you apply L'Hopital's, it looks like the right answer is negative infinity. So why did L'Hopital screw me up? It wasn't L'Hopital's fault. We used it when we weren't allowed to use it. L'Hopital's only works if the thing I have is indeterminate. If we apply it, it's like L'Hopital says, screw that. I have nothing to do with it. It's your own thing, whatever you get. Leave me out of it, right? You guys with me? So it's not even like you did more work than you should have. It's actually you might have made an entirely wrong problem now. Do you see that? So it's not even like, oops, no, it's now entirely wrong. Yeah.
Is that pi from the negative side?
Yeah, from below.
Alright.
Yeah. Okay.
So it's just 0 over 0 is indeterminate?
Or infinity over infinity. Or, let me kind of collect a few. So we got 0 over 0. We have infinity over infinity. We have infinity minus infinity. Right? And then we have 0 to the infinity or infinity to the 0. And that's the last two types. Right?
Would infinity plus infinity not be up there?
No, because that would just be infinity.
Well, these are indeterminate, right?
Indeterminate.
So
Wait,
0
it says right here, although the forms type of the type, it says 1 to the infinite power are indeterminate. But how does that?
Oh, yeah, that's the last little piece.
Why is that?
That would be, here's an example of that. It's not, you got to remember, where are these infinities and zeros coming from? They're not coming from the problem, they're coming from the limits of what's in the problem. So if I had a problem like, limit as x goes to infinity, 1 minus 1 over x, to the, what do I want to make this? To the x. What's the limit of the inside?
1 of x.
As x gets really big, what happens to this? Goes away. So the inside's 1. And the power, of course, is going to infinity. Cool. Right? So how can I work with this? What can I do? And it's sort of like what we do for these guys here. And that's what they have started on page 306. In the middle of the page, they start with these guys. So what do you think I can do with this? What's the only thing we have that helps us with variables that are up in the power?
Why wouldn't that just be 1?
It's not. And here's why.
Okay?
If this ever got to 1, I completely agree with you. Does this ever get to 1? It's always something slightly above 1, always. So it's something slightly above 1 to something that's getting really stupid big. So maybe it goes to infinity. So you have two different competing things here. Maybe it's 1, maybe it's infinity. What it ends up being is something in the middle. And that's kind of like where they compromise. They say, okay, I'm getting really big, you're not getting anywhere. Let's meet somewhere in the middle. Yeah?
How did you say that? Isn't that less than 1? What's it there?
Oh.
It's the higher x.
This is becoming really, the number itself is becoming really small enough.
Say again?
It's like anything but 1, if it's multiplied with each other, it'll get a little bit smaller than 4, right?
If it was, yeah, if I left it the way I had it. Yeah, it should be the other way around. Thank you, though. All right, so how do we analyze this? It's actually exactly the way we analyze those over there. What's the only thing that I have that helps me when I have variables up in the power? Natural log, right? And who knows how to rewrite, let's see, what can I say here? Yeah, this is fine. So I can rewrite this using E and ln. Or 10 and log, for that matter, but we normally use E and ln. And the way I can do that is just like this. So think about that. Is that true? Not just because I wrote it up there. But that's obviously true. The E and ln would cancel, you get x. Right? There's a little bit of, the absolute values and all that kind of crap. So here, if I rewrite the inside as e to the ln of this, the x, of course, could come down. So now what form is this in? Because now I can bring my limit inside. So I got e to the limit. And I'm allowed to do that because e is a continuous function. I can bring the limit inside. I don't know if you guys remember that. And what form is this in now? What's this going to? Think about it. The inside's going to 1. What's natural log of 1? 0 times infinity. That's one of our indeterminate forms. Right? Did I put it up there? No, that's one I left off. There. So, how do I work with that then? What do I do? We really asked for it now, yeah. So what's wrong with this form that it's in for me to apply what I want to apply here? What's wrong with the form that this piece is in? Don't worry about the E dude. He's just hanging out until this figures itself out.
It's not a ratio.
It's not a ratio. So what's the easiest way to make that into a ratio?
ln of 1 plus 1 over x, all over 1 over x.
I like it. Now let me see if I want to show you the trick. Let's see, will that work? Yeah, it would actually. Let me show you a little trick. Because that looks, can you imagine doing the derivative of that? I mean, it's not horrendous, but it's not all that nice either. There's one little thing I could do with this. I can make this natural log of x plus 1 over x, and then I can break it up using the properties of logs and so forth, blah, blah, blah.
Say that again? You can make it what?
So I can make it, let me see if this is really difficult to do. This will be natural log of x plus 1 over x, just getting LCD. Which will be, what can I do there? Yeah, the quotient rule, so it'll be, not quotient rule, real not derivatives, but the quotient property of logs. Right, when x goes to infinity, this is still a problem. It's like infinity minus infinity over 0. It's still a big problem, right? But now I'm curious about that. Is that all right? That's not the way I was thinking about doing it first. So you got that way. Let me show you a little bit better one. Because now I'm not so sure we can still apply what I want to apply here. Let me show you something based on what we were talking about earlier about when I proved L'Hopital's rule one way, and then it just said if it's going to infinity, all you got to do is turn the sucker around. So look at what I got here. This is kind of like a good clue as to when to do that. If I let t equal 1 over x, and people always feel like this is cheating, but I am told, what is 1 over x? I don't know. Let me call it t then. I'm allowed to call it a variable if I want to. So if x is going to infinity, t would be going to 0. There you go, right? Right? Mm-hmm. So how does this look now if I do that? This would be e to the limit as t goes to 0 of natural log of 1 plus t, right? Is that cool? Because 1 over x is t over t. Because 1 over x is t. Now that, it's still indeterminate, Let's check it out. If I plug a 0 and I get natural log of 1, which is 0, t goes to 0 is 0, indeterminate. So now I can still apply L'Hopital's to it. L'Hopital's doesn't care what variable you have in there. So if I use L'Hopital's, what happens on the top? Yeah, 1 over 1 plus t, and the derivative inside is just 1. Is that cool? Because the coefficient there is just 1.
Right, so that's right.
Over
1.
1. So let t equal to 0, what do I get? A whole bunch of 1s. 1 over 1 over 1 is 1. So that is actually the definition of E. That's where E comes from. E is the limit. It's the compromise. It's kind of cool. It's the compromise for this problem that I've just completely forgotten. How did I do that? Just too many middle steps here. It's the compromise between, well, it should be 1, because it's going to be 1 to a power. Well, no, it never quite reaches 1. Shit. Well, then maybe it's infinity. Well, no, because it's getting really close to 1 in there. Shit. So the E is the compromise. It says, let's all meet here. And that's why E was given its own symbol, because they said, that's weird. Right? Like pi. Any circle you draw, suddenly you take a ratio and it's always pi. Oh, shit, let's give it its own symbol. Right? Okay, maybe. So I like that example. It kind of shows you a couple things.